Hello, welcome back to this series where I show you how to do basic quantum mechanics problems just using the videos in this series. And in this video, we're going to use the idea of photon energy from part 2 to look at photon momentum. I have a very interesting example that we'll have a look at for that. But then we'll transition using that same concept to look at one of the weirder steps in the history of physics, which is treating matter as a wave. Okay, here we go for part 3, and I am ready. I have my coffee, and because our example for photon momentum is actually going to be a bit of an astrophysics problem, we're going to do some of the actual math behind what is currently one of the more promising prospects for interstellar travel. So I got my space shuttle mug, kind of hard to see on there. It is about 20 years old, but that is STS-1, so the first space shuttle mission right there. Okay, so I mentioned we're going to look at photon momentum using photon energy that we discussed in the last video. And actually that was the second challenge problem I left you with in the last video. And what I asked you to do was to use momentum, P equals mv, and also rest mass energy, E equals mc squared. And combine those two to try and find, well, combine those two and the equation we made for photon energy, which you can plug into there, which, just to remind you, was E equals hf, or also you could write hc over lambda, and combine all three of those and come up with an equation for photon momentum. But to do that, you have to cheat a little bit. And this is kind of one of the earlier ways to figure that out. But you have to pretend that a photon, a light particle, has mass, which we know is not true. We know that photons are massless. So another way you could do that is actually use the full version of E equals mc squared. So this is for something not moving, rest mass, right? But the full equation for E equals mc squared is actually E squared equals pc. I'll just kind of put those two together, squared, plus mc squared, and that's squared as well. So that's actually the full picture when you include momentum in the energy there too. So we can again use momentum and find the actual momentum of a photon, but this guy will be 0. So a little more accurate here, we're saying that because the mass is 0, that whole term drops off. So we'll go ahead and plug in the energy on this side. So now we have, and let's go ahead and use wavelength. So we have hc over lambda squared. That is equal to momentum times the speed of light squared. And then you can just take the square root of each side. So those guys go away. You can also divide a c after that. So those guys go away. And then you get our momentum for a photon is simply h over lambda. And you could also, again, switch out lambda there with frequency, using the relation we talked about. I think that was part 2, where the speed of light is always equal to frequency times wavelength. But there's our equation for photon momentum, and that's also what you should have gotten for the challenge problem, combining those three equations at the top. But this is a way you can do it and actually say, okay, yeah, photons don't have mass, but you'll arrive at the same answer. And this is very interesting because you'd think, using classical momentum up there, well, if a photon has no mass, it should have no momentum, right? And some of you may have thought that working on the challenge problem. So, but it actually does have momentum, as we see in this relationship here. So momentum doesn't just depend on mass. So this equation isn't entirely correct. And if you apply it to a photon, then you'd say, oh, it's got zero momentum, but they do in fact have momentum, and you can use that momentum as a pressure and as a force. And that is the whole idea behind the example that we'll get to. So next up, let's go ahead and figure out how much pressure or force you get with the momentum of a photon. If you open up pretty much any good introductory physics textbook and go to the section on radiation pressure, you can find an equation for force imparted by some radiation, and it is force equal to irradiance I multiplied by the area that you're imparting that light on, divided by the speed of light c. Irradiance I is power, I'm writing out power so we don't get it confused with momentum, divided by area. So if we plug that in, you can actually get rid of the areas there, and what you're left with is power divided by the speed of light. And we can use what we've been looking at to arrive at that equation there. And I'm just going to clean this up a little bit so we don't have too much going on. And I'll rewrite. Again, we have force equal to power over the speed of light. And I won't spend too much time on this because that's really all we need, but I think it's kind of fun to show how you can take that idea of photon momentum and realize that it actually will put force on something. We don't really think about that, right? But, you know, if you stand out in the sunlight, there's a little bit of radiation pressure actually imparting a force on you. And we'll use that in our example. Let's have another look at our equation for photon momentum. And we have h over lambda, and that is quite similar to the equation for photon energy, right? And for that we had E is equal to hc over lambda. So to relate these two, let's multiply and divide this guy by c, which doesn't really do anything, it's just a new way to write it. So we get hc over lambda c. Now that's the same as saying h c over lambda times 1 over c. Now you can see that this is just energy times 1 over c. In other words, we now have energy divided by c, speed of light. So that is another way you can write photon momentum. Now let's go all the way back to the first video to look at the equation for force, which is change in momentum, not power, momentum, right, over change in time. and we can plug in this guy. So momentum is equal to E over C. And let's just say change in time is some constant t. So now we have E over t c. And let's actually break these guys apart just to make it a little more clear. Get E over t times 1 over c. What is energy over time? Well, if you saw the last video, you would recognize that energy over time is power, right? So we get power divided by c, and that is the exact same equation. So we have shown that indeed having some photons absorbed into some material, the force is equal to the power divided by the speed of light. So for the example, finally made it, we're going to look at a really fun idea that people have had for pretty quick travel that could actually turn into interstellar travel using solar sails. So let's say we have a solar sail here. And let's say it's going to absorb the light that we shine on it. Some very high energy radiation. It's going to hit our solar sail. And then out of that, we are going to get some force, some acceleration, and some final very fast velocity out of our solar sail. And for this particular solar sail, let's say that we are going to shine a laser on it. And that laser is going to be about 25 gigawatts received by the solar sail over the course of 10 minutes. So to get the total power over that period of time, we are saying our solar sail will absorb about 15 terawatts. Terawatts, what's that? So that is about 15 times 10 to the 12 watts over the course of those 10 minutes. So we know that, and we want to figure out how fast it's going to end up moving. Let's also say we know the mass of our solar sail. Let's say it is very light, nearly 1 kilogram. Then we also know the amount of time is going to be 10 minutes. Now, let's go back to the equation for force that the light here is putting on the solar sail. So that would be force is equal to power divided by the speed of light. And then that is equal to mass times acceleration. Again, going back to video number 1. And acceleration there is what we're going to try and get the ending velocity from. So acceleration, again, going back to the first video, we have change in velocity over change in time. Now for this guy, we're just looking at, let's say it's initially not going anywhere, and then after that force of the radiation, it has some final velocity that it's going at, and time is just constant 10 minutes. So we get start final velocity divided by time. So we'll plug that in for acceleration. We get mv over t. So now we have velocity there. Let's solve for that. So we'll multiply that t over here and divide that m over here as well. So our equation velocity is equal to time times the power divided by mass, and we divide that over, times the speed of light. And we know all of these. Of course, speed of light, just constant, 3 times 10 to the 8 meters per second. So we'll go ahead and plug these guys in. So time, 10 minutes, times 60 seconds, so that gets time in seconds. And power, 15 times 10 to the 12 watts. Mass, just 1 kilogram. Oh, that's nice. It's almost like I picked that on purpose. Then we get 3 times 10 to the 8 meters per second for the speed of light. Let's go ahead and plug these guys in to the calculator. Okay, and there we get our answer, which is 30 times 10 to the 6 meters per second. So that is pretty fast, right? And you can also write that as 3 times 10 to the 7 meters per second. And well, what if we divided that? I mean, that's really close to the speed of light, right? 3 times 10 to the 8. So you can just divide 3 times 10 to the 8, and you figure out that is actually, our velocity here is 10% the speed of light. Yeah, so if we're talking about trying to travel, light years, distances between stars, and our nearest star is about 4 light years away, well, 10%, that's not bad. It'd take about 40 years for this solar sail to get to our nearest star, whereas our next fastest, the fastest thing that we've ever launched is going to take, tens of thousands of years to make that kind of journey. So this is really interesting stuff. And if you look up the Starshot project, that's exactly what they're talking about. But we kind of, we didn't even go the full way, because we said that this solar sail is just absorbing the light. Well, what if it reflected light back out the other way as it gets hit by the laser? Well, that actually increases the speed by a factor of 2. So for Starshot, it's essentially the same exact problem, but they're more reflective solar sails, and you'd multiply this whole thing by 2, and Starshot is ideally going to be capable of 20% the speed of light. And also they don't need such a powerful laser, because they're hoping to bring down the mass even below. They're hoping to get it down to about 1 gram, so 1,000 times less than the mass that we used here. So then you don't need quite as much power imparted on the solar sail. But I wanted to do this example. For one thing, it's just very fun to think about ways we could actually travel such far distances, getting something with a force of radiation up near the speed of light, considerable percent of the speed of light. That's one thing. But also number 2, just to really settle in with this idea that light does have momentum, right? And it can impart a force on something, a considerable force. And that brings us to the last topic of today's video, the very weird way that matter, if you think about momentum of just, not a photon, but an actual material object moving, how that can correspond to a matter wave. So we've been talking a lot about this equation for photon momentum, Planck's constant divided by wavelength, and that's great, right? We think of light as having wavelength, how we see light, different wavelengths or different colors, but physicists about 100 years ago, early 1900s, started to think, well, what if we kind of flip this equation on its head and think about something more classical? So we'll flip the equation here, and we get wavelength equal to h over momentum. Well, momentum we're more kind of familiar with than classical objects, and so we can use that equation, which, as I said, was not entirely correct, but for large, slow-moving things, momentum, mass times velocity. You can plug that in there and figure out what's known as the de Broglie wavelength for an object, for even a classical object, a marker, a person, right? And we can plug that in there, h over mv, and that is the de Broglie, or de Broglie, as I've heard it pronounced, the de Broglie wavelength for some object with momentum. And anything has momentum. When you get down to the smallest of scales, right? Everything is all jiggling around and not stationary. Anything with a temperature is corresponding to fundamental motion of things in an object. But this isn't a thermodynamics series, so I won't go into that. But it's fun to just kind of think about this. So for a classical object, let's say our mass were 1 kilogram, and our velocity is 1 meter per second. Well, let's plug that in, figure out the wavelength of this classical object. Well, 1 and 1 in the denominator, right? It's just 1, so then we're just left with Planck's constant. But in meters, 6.63 times 10 to the negative 34, that's tiny meters. And this is exactly why we don't have to consider the wavelength, right? We don't think about the wavelength of this marker as I hold it. It does have, technically, some probability distribution to it that is spread out, but as far as we're concerned, it's just one thing. But let's kind of scale this down a little bit, so we're not thinking about just a classical situation. And let's look at the wavelength of an electron. And for that, the mass, marker's kind of failing me there. The mass is 9.11 times 10 to the negative 31 kilograms. And for velocity, electrons, they can be moving at all kinds of different speeds and different situations. And particle accelerators, we can get them up a fair fraction of the speed of light. But just for fun, let's use the speed in the last example, which was 10% the speed of light. Or more specifically, let's use 3 times 10 to the 7 meters per second. Let's go ahead and plug that into the calculator, figure out what that electron's de Broglie wavelength would be. Okay, so we get our answer here as 2.43 times 10 to the negative 11 meters. Well, that's still pretty tiny, right? It's still trillions and trillions, way, way bigger than what we got for our classical situation. But this is roughly where we're talking about the scale of quantum and the scale of atoms that we'll be talking about. Things like distance between an electron and a proton in an atom. And keep that number in mind, especially for the finale of the series. But that is when this becomes a little bit more apparent. This idea of matter waves, which will be the topic throughout the rest of the series here. And this is already a very long episode, but I'd like to just end it off real quick with a challenge problem. Okay, so your challenge problem is to figure out your de Broglie wavelength. And you can use the equation we just talked about, plug in your mass, your velocity, however fast you'd like to be moving, and you might have to do some conversion, right? So we're talking kilograms and meters per second. If you're going to use Planck's constant in joule seconds, of course, but you can plug those in and comment down below your de Broglie wavelength. It'll be different for everybody, and if you want to be a little creative, pretend you're an electron or something, do whatever you want, but just to get comfortable with that equation. All right, that is part 3. Thank you for watching, and thanks so much everyone who's kept up with the series so far. I really appreciate it, and I hope that y'all have learned something new. So don't forget to subscribe if you haven't already, and I'll see you in the next one.